Thank you very much. Thank you very much for inviting me. Bogdan, who's here somewhere, Bogdan and I are submitting a survey paper about continuous heterogeneity tomorrow. That's the deadline. So I thought I might talk about like kind of the broader view on like how these different approaches that we've seen for continuous heterogeneity, how they sort of fit together. So I'll talk not only about my work, but maybe mostly about the other people's work today. And part of this is sort of trying to organize these into different groups, different clusters of ideas. And I'm sure that 50% of you will not agree with me about how I decided to cluster this. And 50% of you are going to be offended because I'm not citing your work here. I hope there's a large overlap between these two groups, so at least some of the people here would be happy. Yeah, so we'll see. A lot of people mentioned the models, so I'll just talk about this very briefly. Cryo-EM has been around for decades. I'll mention a paper from the 70s. But what happened in recent years is that this advancement in detector technology really allows us to go to near atomic resolution. And some of the advantages of cryo-electron microscopy, so one of them is that we don't have to crystallize our molecules as we needed to do in X-ray crystallography. And another advantage is that we're really looking at individual molecules, individual particles, which means that we're not measuring sort of an ensemble of particles like we do in X-ray crystallography or nuclear magnetic resonance. And that gives us at least the hope that we could identify different conformations that appear in mixtures. And really, like the motivation for this is that these are sort of molecular level. These molecules are essentially machines, and if we want to understand their functionality, their movement is what we're really interested in. So I tend to use simpler examples than others for this. So this is my cat. And today, I'm also going to use the figure of Wonder Woman. So you can think about this having these multiple conformations where there's this pieces that are moving around, and they perform some functionality. If we had just this, if we didn't have a sort of a representation that gets all these different conformations of Wonder Woman, we wouldn't know that she can move her arms or legs, etc. Okay. So the traditional solution is basically to try to discretize this. So try to look at these different conformations sort of in isolation from one another, essentially. And usually we kind of think about them as sort of aligned, but they don't necessarily need to be aligned. They're kind of, it's kind of these independent models. And if to put a little math on this, people talked about it, so I won't talk about it that much, but we have these multiple models here. Each one of them represents a volume. Each volume is some kind of a sum of some basis functions. We usually think about, in most algorithms, it shows up as some kind of a grid that we're interpolating on. And we have some kind of a forward model for if we choose one of these volumes and randomly choose some viewing direction and CTF, et cetera, and noise, we have a forward model for this, which kind of means that we can at least formally write some kind of likelihood of the images given the data, and we can sort of turn this around and try to find the maximum likelihood model given, or maximum likelihood models given the images that we see. So that's what. So that's the traditional approach to heterogeneity. It's to discretize, and it actually works very nicely if you have very distinct conformations. But what we're trying to do here is go beyond this to continuous heterogeneity, where you have some kind of flexibility in our molecules. So I'm going to talk about, I'm kind of dividing this to about 6 families of algorithms. I'm going to skip these manifolds of volumes and these and the the normal modes, just in the interest of time. They're also very interesting. But so let's start. So, and again, like I said, I'm going to omit a lot of details and probably piss a lot of people off and like how I organize things. Oops. Okay, so let's start with these manifolds of images. So that's one of the earlier ideas for how to treat continuous heterogeneity. So the idea there is that we can think about some kind of a manifold of volumes. And the insight that they had, the people developing this approach, was that if you have this manifold of volumes, you can, if you look at the different viewing directions for each one of these volumes, you get this manifold of the viewing directions multiplied by, so this product of viewing directions and the conformation space. So you get this product of manifold, and that is also a manifold. So you could take all the different images and try to do some kind of manifold learning on them and try to infer all the different conformations. There's a lot of difficulties in this because it's sort of a huge number of images that you kind of need to compare to each other and try to construct a manifold from them. And it's very difficult to sort of separate the different orientations from the conformation. So what happened? So the way that it evolved is that what they do in this approach is that they assume that they know the orientations, the viewing directions, and for each viewing direction they build a manifold of the images that they see from that viewing direction. And then they try to stitch these manifolds together and build sort of some kind of a consensus manifold and kind of learn the landscape of conformations on this map. So there are still a lot of challenges in these methods. Some of them have been addressed here, but I want to really actually go back and touch the kind of the fundamental issue with manifolds. It's not a criticism about this method. Some of these issues with manifolds, we'll see that they sort of apply to all the other methods that we're using. So let's take like a step back and talk about like manifold learning on some kind of generic scientific problem. So I'm going to have an action figure on a spinning table. Here it's going to be this. Here it's going to be this figure of Wonder Woman. And in the simulated, so we actually did this with like an actual camera and everything. But in here, what I want to show you, whoops, spinning, no. Okay, I'll fix that later. Luckily, that's why we have simulations of these. So here we simulated this with a horse. So that's something that Bogdan did. Sorry? So this is a simulated horse, okay? Importantly, not a spherically symmetric horse. What you do is we have this horse in different orientations. So that's these different directions that the horse takes. That's like the different physical states, okay? We're sampling them uniformly, okay? But we don't really observe directly the viewing directions. What we observe is some kind of a measurement. This measurement in this case is this thing. So it's these. I'll explain this with this. So I have a camera. So okay, and the camera is taking images of the horse or of Wonder Woman, and that's our physical measurements. Okay. So we take these images, we throw them into our favorite dimensionality reduction algorithm. For example, I like diffusion maps. It's also the algorithm that's been used in these manifold methods. And what we would hope to get is this kind of manifold representation that gets us the topology of the problem. So we have something kind of looking in any possible direction. So the circle is a representation of this topology. And we would also probably want to get something about the, so this is, we know that this comes from uniform distribution of horse looking in different directions. We would also like to learn something about the distribution. So let's do this experiment. So again, we're taking these, this is like something we don't observe directly. We have these horses looking in different directions, uniform distribution. We're taking these images, and if we run, and if we throw these images into manifold learning, yeah.
Just a very short question. What is the distance measure that you assume?
That's extremely important. That's extremely important. So in here, the measure that we assume for distances between images is just the L2 distance between images. But that's an extremely important point. I'm going to get back to it in a moment. So if you throw this into diffusion maps, you get this beautiful circle, okay? But if you look closely here, you'll see that there's a higher density in certain regions. So if you were to ask me, are there like dominating states here? I would tell you yes. There are these regions here that have a higher density. We know that it's not true, but that's what I would tell you based on this. It actually gets worse, because if I take a different modality, so instead of having the camera here, I'm going to have the camera here, okay? And we take these images of the same states, and we do diffusion maps on them. Again, we get a beautiful circle, and again, it has these regions of high density. But these regions of high density sort of are connected with other physical states than what we measure here. So it's kind of, so both solutions are wrong in a sense, and they don't agree with each other, okay? And basically the reason behind it is the metric. The metric in this experiment, the metric of the images, these images of the horse actually depends on the viewing direction. It doesn't directly reflect the physical angle that we kind of would hope maybe that it reflects. So exactly to your question, okay? So the point is, in the context of these manifold algorithms, this manifold analysis of images, of course, it's more complicated. It's a little more complicated in toy horses. There's more noise, etc. Okay, but there's two places where it appears. One is that we have to take these manifolds in different directions, and as we've seen, they might not agree exactly with each other. So there's a lot of work that goes into the stitching, and in the recent versions of this, they do a lot of work on that, like how to stitch in the best way. But there's another problem that kind of influences all the other algorithms that we'll see as well. At the end, we try to get this sort of a manifold with kind of densities and say, okay, there are like this dominating state here, there's like this dominating state there. We're trying to find this landscape from this map that we infer from basically all the algorithms that we've seen. And these maps, they're usually like, so for example, they can come from some variational autoencoder. What's the metric there? I don't know. And on top of this, maybe we're doing UMAP or something to do dimensionality reduction of this. How does that affect the metric? I don't know. And you know, if a horse is a problem in this case, we might run into problems here as well. We might, like, you know, an expert might look at these and be able to interpret what's going on, but you know, the more complicated these models are, the more complicated heterogeneity is, this might become more and more of a problem, how to interpret these maps that we get from basically all these methods that we're going to talk about, okay? Any questions about this?
Let me, as an author of that paper, let me counter.
It's not about that paper. I'm saying there's a lot there's a lot that's been done to address this, right?
No, that's correct, and thanks for telling that, because it's true. Like, this orientation has been a problem, and so orientation-dependent metric should not be taken. Like, something like a distance metric would be a better idea, where the orientation of the particles itself does not come into being. So that problem is addressed. Now, the interpretation of the landscapes that you mentioned, that is questionable, and that, of course, depends on the domain. I think the bigger problem that you forgot to mention, let me help you. So these values, the barriers and the energy valleys of a landscape, it's in a very weird conformational coordinate. So normally molecular dynamics simulations, any biological entity works in barriers of 10 kBt, 6 kilocals per mole. If you would have shown the magnification of that image is higher, you would have seen these numbers to be really, really small. So might be the problem is it's an oversimplification, an over-smoothing of what the...
And I think one of the issues that I didn't want to go into all the possible things, but these issues that, by the way, I think affect all the methods that we're talking about, not just this approach, is probably that we don't really, the latent variable that we learn for the conformation, so for each image where it is on this map, it's probably not that accurate. Like, that's kind of inherently, so it naturally smooths out. I didn't want to go into this, but I think that's an important, another important aspect of the issue. Yes.
So in this space, we don't understand energy, even though we're plotting energy, and we're telling that the number is a very small number, but it's very difficult to understand what does energy mean in that space, because energy is a function of a reaction coordinate at one level.
Yeah, and in this case, this metric doesn't necessarily conform to.
I think that is possible. Little more subtle way of criticizing this, but thank you.
Thank you. So again, the point isn't criticism. It's like some of these challenges that I think in some of the later work are part of what you're addressing there. Okay, so that was brief about manifold of images. One of the other ideas that came very early was these models that are linear in volumes. So what do I mean? So we have each volume in this conformational space is represented by as a sum of some kind of a mean volume and some linear combination of volumes. These would usually be principal volumes. So these are the principal vectors of the covariance matrix of the volumes. The original work in this tried to sort of bootstrap it way into finding into like some kind of collection of volumes to take principal components of. But of course, Cryo-EM data comes in two-dimensional images, not volumes. So one of the remarkable results, due to some of the people in this room, is that you actually don't need the volumes in order to get the covariance matrix. It turns out that it's enough to just have these two-dimensional images, and you can get the covariance of the volumes directly from that. And this captures a lot of the variability. One of the sort of iteration on this is this 3DVA that's available now in CryoSpark. I want to show you and it's actually pretty successful, especially if there is kind of still distinct conformations. And I want to show you a sense of like what's the difficulty with these linear models. Especially because the traditional way of visualizing the result out of this, it's not the only way, but maybe the traditional way is to look at each mode separately. So you get several different principal volumes, and you look at each one and you take like this average plus some kind of like scaled scaled version of of each principal volume. So let's look at a very simple experiment. We have this mass that's sort of going around in circles. What do you think is going to be the principal components of this? So right. It's actually, if you kind of look at this, you can actually get this analytically, but it's sort of surprising the first time you see it. So here these are. Here are the principal. Why isn't it clicking? Okay. Okay, so these are the principal volumes, and that's if we visualize them this way. And the reason is that the actual valid states are some kind of linear combinations of these, and not every linear combination is valid. Okay, so this looks very different from this, which is one of the difficulties in these linear models. And I'm not talking about this here, but there is a lot of work that's sort of trying to kind of combine, for example, manifold learning, work by some of the Amits in this room, combine manifold learning with these to take this sort of to the next level. But this is one of the issues with the linear models. So again, I'm skipping normal modes. Normal modes would get this, what Stephen here was thinking would be the normal mode. These are the normal modes in these models. But I'm going to skip these, and I'm going to talk about nonlinear models. And so let's revisit first what's the how we used to the traditional way of analyzing cryo-electron microscopy data. So like we said, we have these independent models. So independent discrete models. And each one of them is usually some kind of a sum of some kind of a linear combination of some basis functions. But there's something not very pleasing to the eye for most humans in this. And this might be a little bit more pleasing for us. And I didn't do anything mathematically. All I did is I organized them in the right order, and I aligned them. But these are independent models. Mathematically, I didn't do anything. Okay? So why is this more pleasing to us? Because there's some kind of smoothness in the transitions between these models. And we can capture this actually mathematically. For example, if we take if we turn this into a four-dimensional function, and we take these basis functions that are sort of smooth along these directions, this would be a better solution than these things that sort of run around all over the place. And this sort of visual pleasing thing, smoothness thing, is actually, you can think about it as some kind of regularization, for example, that makes a difference between the smooth transitions between different volumes and these distinct independent conformations. So that's a model that we called hypermolecules, this higher dimensional version of a molecule that in one model tries to capture all the different conformations. Originally, the way we described it was as sort of in the traditional as the traditional analysts, as some kind of a linear combination of basis functions. And solving this problem means solving the coefficients for this linear combination. And there are these nuisance variables that you kind of want to get rid of, the orientations and the conformation variable. So that's one way of representing them. That's the original cat from that experiment. Like you throw in, was this very silly kind of gradient descent type algorithm that takes images, you don't know what the orientation is, you don't know what conformation is for each one of them, and it infers this cat, and it infers this continuum of different states. It's very interesting. It's not aligned the way we might expect. Apparently it finds a better alignment, but so the cat is dancing also. And so that's one way of writing these hypermolecules. What Cryo-Dragon does, and I don't need to talk that much about Cryo-Dragon because it was presented today. There's I think two big innovations there. One is this completely different way of representing the functions, not the way analysts would usually do. So it's represented, the function itself, this hypermolecule, is represented using a neural network with these positional encoding that Ellen talked about. So that's one innovation. And it has some advantages, for example, in going to higher dimensional conformations, etc. And the other thing, so it's a variational autoencoder architecture. So it has these two components. One is the decoder. So that's this, what I call hypermolecule. It's a different way of implementing it. The other thing, the other innovation is the encoder. So in the old days, the way we used to think about all the latent variables is that we're, for example, trying to estimate them. We're trying to find the best orientation, or we're trying to search over all the different orientations for each individual image. And instead, what's done in Cryo-Dragon and subsequently in many of the other work on this is, instead of like sort of memorizing, for example, and updating a variable for each one of these images, each one of these images goes into an encoder, and that magically spits out the variable. And one of the nice things about this, in principle, is that at least naively you would expect that you can actually learn this variable for images that you've never seen. So I want to show you some anecdotal experiment with this. And again, this isn't about criticizing Cryo-Dragon, which is great. It's just like things that for us, we had a naive interpretation of this, of what's going on there, and we tested it, and it's not what we thought. So for me, it's like there's all these things that we still don't know about it. That means like possible things that we can improve or can take from this and improve in other methods. So one of the things that you get out of these encoders is amortization. And so you can put in any arbitrary image and get out the latent variables. My naive interpretation, it can generalize, and it should generalize to images that it's never seen. And actually, we're sort of lucky in Cryo-EM. We have this sort of natural test case. You can just take the image and rotate it. So we took the image. So we kind of did the optimization in Cryo-Dragon, and then we take the image and then we rotate it. And it goes to a very different place in the state space. Which doesn't mean that Cryo-Dragon doesn't work. It just means that maybe it's like not a naive interpretation of this isn't accurate. It works without necessarily having this generalization that we might naively expect. And another naive expectation was that it's very different from having the explicit an explicit variable attached to each one of the images. So again, we're very lucky that Ellen is very generous and provides the very well documented and very nice code for Cryo-Dragon. So we took Cryo-Dragon and abused it a little bit in several different ways. There was a paper coming out about this. And we replaced the encoder with this table of latent variables that we just, in stochastic gradient descent, optimized for each one of the images. Just like replace a piece of Cryo-Dragon with actually based on other code that was already existed in Cryo-Dragon. And it's slower to optimize, okay? But if this is the results from the sort of vanilla version of Cryo-Dragon running on tutorial data set, this is what you get if you run this with explicit variables. And it's at least qualitatively very similar. I don't know what it means, but it's sort of, to me, like there's something there that we don't entirely, or at least naively don't understand exactly how it works, and there might be something to learn from this about how these variational autoencoders can be used in the problem and how they can be improved. Okay, so both these models, like these linear combinations of basis functions or these neural network implementation of this, they're very generic. They can kind of generate any sort of weird object that you can think of, but in practice, it becomes a liability in a sense when you have very complex heterogeneity. And to give like one of the motivations for the problem and sort of why we need to impose structure, I'll give a very simple example. So again, I'm going to use the figure of Wonder Woman for this. So there's these different pieces that are moving independently, okay? And so there's like at least these 4 limbs that are moving independently, okay? And if you start counting the number of coefficients that you would need in order to represent this in sort of a very naive way of counting it, and it sort of corresponds to the number of images also that you would need in order to fit this, what you see is that it grows exponentially with this simple measure of complexity of the problem. But if you impose a very simple model, for example, if we look, so here we have this thing with 2 arms flapping around. But if we look at the anatomy of this thing, we have a rigid object with these 2 different distinct regions that are heterogeneous. If you count the number of coefficients that you need in order to represent this, you see that they grow linearly. Actually, you see that it's actually constant. It doesn't even grow linearly, but that's a little bit more nuanced. So modeling can help us in sort of improving our algorithms. So this is something we did originally with this idea. And it definitely evolved from there. So one approach for modeling has been that evolved was deformations. So you have some kind of a reference model, and everything else, all the other conformations are deformations of this reference model. We had a version of this with Carlos Oscar, and there's a version of this that Ali Punjani and David Flitt wrote that uses neural networks with like these neural flows. And that's a model. You have a reference object, and you're restricting yourself to these deformations of the reference model. Things can just appear and disappear everywhere. Another approach for modeling, which actually is at least most of the work has been done earlier than this, is using the GMMs that Steve talked about, and there's and so this is from the original paper, and now there's some new work coming out that I didn't know about that Steve presented today, and there's other work that sort of scales this to higher resolution and impose additional modeling that Chen did, and we helped in some of the scaling there. And maybe, in a sense, the ultimate model here is that we really have a molecule, and there's like these chemical bonds there. And very often we know what these are. So this is this work that came from the AlphaFold team with some ideas from AlphaFold was to really write these functions, which are basically these GMM models, but imposing these. I think I can put this down. But imposing these chemical bonds between the different atoms in the molecule, imposing the actual atomic structure. And that's so far been done, I believe, only in simulated data. But there's some difficulties in applying it to real data still, but possibly that's where we're going, sort of to this ultimate form of imposing structure. Finally, I want to mention, so in all these other in all the methods we talked about so far, there's a ton of these latent variables, and we try to estimate, or we have an encoder for them, or something like this. And then there's this two other approaches that for heterogeneity that are that kind of completely sidestep this, and I'm going to explain them actually just for the homogeneous case, not for the heterogeneity, because in the homogeneous case we have this issue with viewing directions. And what Zvikam observed in the 70s, 77 I think it was when the paper was submitted, was that you could actually just take the tomographic projections, compute moments from them, and from these moments you can recover the 3D object. And there's additional, more recent work that kind of builds on top of this. And for example, some of this work shows, people in this room, shows that you don't even need to do particle picking. You can just go directly to the micrographs, compute moments, and get the molecules out of this. This idea generalizes to heterogeneity. It's maybe a little bit more complicated, but the idea is sort of similar. From these moments, get all the different conformations of the molecule. So that's one approach that's based on matching the moments of our model to the moments that we observe in our experiments. So it's kind of trying to match the distributions. A completely different approach for matching distribution is this Cryo-EM thing, where they're doing, they're trying to match the distribution of the observed images using, they're trying to find a model in sort of this GAN architecture. They're trying to find a model that would have produced the same distribution of images that we see, without ever figuring out the specific viewing direction or for any individual image. If you think about it, it's sort of crazy in a way because there's so many latent variables in factors. Like in this case, you would also think about CTF and the translations, and remarkably they can demonstrate this, and at least in some examples. Not only that, they actually also demonstrated this to some extent on continuous heterogeneity. So you never actually compute these latent variables. You just try to match the distributions, and you get the models out of this. So all these solutions, problem solved. So first of all, I want to remind you of the horse in the room. So analyzing this, especially as we go to more complicated, so this is just one example of one of the challenges that sort of on my mind, especially as we go to more and more complicated heterogeneity. There's this question of how we interpret these maps and how they relate to actual physical states. By the way, even different algorithms wouldn't produce the same map, right? There's no reason. Even different runs with different seeds of the same algorithm wouldn't produce the same map. So we can't even compare them. And basically what I'm saying, problem isn't solved just yet. It's I think in many ways this is sort of the early days of continuous heterogeneity. There's a lot of ideas. I always think we kind of covered all the ideas, and then there's another idea that comes up. And there are a lot of issues that we barely started touching, like even just identifiability of this problem. Like, is it possible to get the different conformations without a ton of assumptions? How do we validate any of this? There is this idea of like taking subset of the images, but is this enough? How do we like compare even different outputs of different models? What's the kind of a quality metric of anything here? Like FSC doesn't make that much sense anymore. If we want to compare different algorithms, we also need some benchmarks. We don't have any benchmarks really yet. So it's really the early days of this area, I think. I want to mention that unrelated, I want to mention that we have these monthly seminars that we started during the pandemic. They're mostly focused around mathematical, sort of the mathematics of Cryo-EM, but there's sort of a wide variety of talks there. We started this during the pandemic. Now it keeps going. If you want to get the announcement, they're on you can go to cryo-em.world and register to the mailing list. It's only announcement. People can't just send random message on these. You get like one announcement before the talk and then one reminder with a Zoom link, and that's it. So feel free to join this. And again, I want to mention Bogdan over there. And we did a lot of this together. And there's the actual review paper that I mentioned that we wrote is going to be submitted tomorrow, so it's going to be on archive sometime probably this week. Also, Bogdan has a poster if you want to learn more about rotating horses and how they're related to real world problems. You can talk with him at the poster. And that's it. Thank you very much.